Section 7 out of Chapter 23 deals with transformers. One of the most ubiquitous uses of transformers is in the process of power transmission. Power transmission is how I get electricity into my house. So there's a generating station somewhere that produces electricity through a process of some mechanical thing, whether we're boiling water or letting wind blow across fan blades. There's some process that's turning a shaft that's connected to a generator. That shaft is attached to wires, coils of wire, inside a magnetic field, so as it rotates, it generates an EMF. That produces a voltage which causes current to flow. So the generating station produces electricity, and it produces it at some voltage, some EMF, that depends on the processes going on here. That voltage, I want to run things in my house, so they have to transmit power to my house. Remember that power in electrical circuits is equal to current times voltage. I want to transmit this power from one place to another. As I do that, though, as the power goes from the generating station over to my house, it has to travel through wires, and those wires have some resistance. And so there will be a loss of power due to the resistance of the wires, which will be I squared R. Now, the resistance of the wires is determined by their material and their length, and there's not much we can do about that. But this current, if we had a way to modify the current, we could reduce the lost power during the transmission process. So power is current times voltage, and I'm going to transmit a certain amount of power. My house requires a certain amount of power, so I'm going to need a specific amount of I times V. But I want to minimize I. So if there were some way I could change V, specifically increase V, so that I decreases, then I would decrease the loss that occurs during the transmission process. First of all, it's generated at 12,000 volts at the power plant. I don't want 12,000 volts at my house, so no matter what happens, I still need to reduce that voltage. There's a process that can do, or actually there's a device that can do that, which is called a transformer. A transformer is this picture physically, this schematically. It's in a lot of cases, it's a coil of iron. So these are square iron plates. And around the leg, one leg of this square piece of iron is a coil of wire wrapped around that. On the other side, I have a different coil of wire wrapped around the other leg. What we do is we connect our voltage source, our AC, alternating current source of power, to one side of the transformer, and that, because I've got current flowing through this wire and the current is changing, it will create magnetic fields inside the coils that are changing. Those magnetic fields follow this path through the ferromagnetic material, through the iron, and they pass through the coil on the second side. So on the second side, I connect this to my house, or whatever device is using the power, and there will be current flowing in this wire because of Faraday's law. I have a flux, there's a magnetic field through this coil, and because the B field is changing, the flux is changing, and so that produces a current, an EMF, a voltage, which produces current flowing in these wires, in this circuit. The current that comes out of this side, which is called the secondary side of the transformer, the other side is called primary. So primary power comes in, and then the secondary power comes out. On the secondary side, the EMF on the secondary side is going to be Faraday's law related to the change in flux over the change in time times the number of coils. So the EMF, or the voltage, on the secondary side is going to equal N sub S change in flux over change in time. On the primary side, the voltage that is produced or that comes into the transformer on the primary side will create a magnetic field. Now, you have to go through the derivations of, given a current, what magnetic field does that create? Given these coils of wires, how do I find the magnetic field inside of a solenoid? But eventually, you get to the point where the voltage on the primary side is also related to the number of turns and the change in flux. This is not necessarily Faraday's law, it's something different, but the voltage is creating a changing B field, and the voltage is related to the B field through this relationship. This gives me a way to analyze the transformer. If I take the ratio of these two equations, the change in flux over the change in time is the same in both cases, and so they cancel out. And so I get this equation that tells me how to analyze transformers. That the ratio of the primary voltage to the secondary voltage is equal to the ratio of the number of turns on the primary side to the number of turns on the secondary side. NP is the number of times that the wire is wrapped around this side. N sub S is the number of times the wire is wrapped around this side. For most transformers, the power in is very close to the power out. There's very little loss here. So I can write power in equals power out. And remember, power is current times voltage. So the power coming in is the primary side. So current in the primary side times voltage in the primary side equals the power coming out, that's the current in the secondary side, times the voltage in the secondary side. So rearranging this equation, I get this ratio, and I can take that and combine it with the equation up above, and I can show that the ratio of the currents, secondary to primary, is also equal to the ratio of the number of turns in the primary to the secondary. Going back to the initial problem of power transmission, how does this help us? Well, this shows me that it's the power that's constant. So in a transformer, I can change from one side to the other. I can change the voltage and the current. So if I increase the voltage by selecting appropriate primary and secondary numbers of turns, I can go from, for example, up here in this picture, 12 kilovolts up to 400 kilovolts. That is a step up, or a multiplication of 33 1/3. So I've stepped the voltage up by 33 1/3 by wiring my transformer with 33 times the number of coils on the secondary side to the primary side. That'll give me a voltage on the secondary side that's 33 times as big as the primary side. So then that turns 12 kilovolts into 400 kilovolts. Now, I don't gain that for free, because what happens is the current will, in a similar way, be reduced by a factor of 33. So whatever current I have flowing in the wires on this side of this step-up transformer, I'll have 1/33 or 1/33 times the amount of current in this side, which is what I want. I want to reduce the amount of current flowing in these wires to reduce the amount of I squared R power loss that comes over here. Obviously, I don't want 400 kilovolts coming into my house, and so once I get close to my house, then there's a step-down transformer where I change the 400 kilovolts down to 13 kilovolts, and then this gets spread out to the neighborhood, and then at an individual house, the 13 kilovolts then gets stepped down to 240 volts that comes into my house. So let's take a look at an example. In the picture at the top, we have 13 kilovolt power lines going through a step-down transformer to end up at 240 volts at my house. Question A, what is the ratio number of turns on the primary side to number of turns on the secondary side of the transformer. Question B, if the current coming into my house is 30 amps, what is the current flowing through the power lines into my transformer? So let's draw a picture of this. So part A, I have a transformer, primary side, secondary side, and I have 13 kilovolts on the primary side, 240 volts on the secondary side. The equation that relates these is the ratio of the primary voltage to the secondary voltage is equal to the ratio of the primary number of turns to the secondary number of turns. So just plugging in the voltages, the primary voltage is 13,000 volts, the secondary voltage is 240 volts, and that gives me a ratio of 54.16. So that's the ratio of the number of turns on the primary side to the number of turns on the secondary side. So if I were to build this transformer, I would want to put 54 turns roughly on the primary side for every turn I put on the secondary side. If, for example, the number of turns on the secondary side of my transformer is 10, then the number of turns on the primary side will be 542. Part B, if the current coming into my house is 30 amps, what is the current flowing through the power lines into my transformer? So the relationship between the current and the number of turns is opposite to the way the voltage works. So the ratio of the secondary current to the primary current is equal to the number of turns on the primary side to the secondary side. We know this is 54.16, and the secondary side, which is coming into my house, is 30, and the primary side is what's coming into the transformer. And so there's a little over half an amp flowing into the transformer, although flowing out of the transformer is 30 amps.